So hello everyone, let's start the last unit of this course today. So up till now we have seen about the static characteristics of CMOS inverter and then the dynamic characteristics. Now let's move on to the combinational circuits, because the inverter is the basic building block of any of the combinational circuit or the sequential circuit. But the complex circuits which we use are not just the inverters but the other circuits as well. So these circuits are classified as combinational circuits and sequential circuits. So here today in the last unit we are going to see the combinational circuits only, not the sequential circuits. So sequential circuits are a little bit difficult, not, I shouldn't say they are difficult, but they need more understanding to understand. They need more understanding of these basics than to understand those sequential circuits. So that's why I'll just cover the combinational circuits and the various things which are remaining. So those things we are going to cover here. Okay. So you see, we from our digital electronics course we know that any digital circuit can be categorized as a combinational circuit or can be categorized as a sequential circuit. So what is the difference between a combinational and a sequential circuit is that a combinational circuit is a circuit whose output depends upon the inputs only. Okay? Whereas the sequential circuits are the circuits in which the output depends not only upon the present inputs but also on the previous inputs. Okay, so the output is like fed back. Okay, so it is so when you do this it have some memory element as well, and when you feed back the output, so then it becomes the sequential circuits. So here, as I have told you, that we are going to see the combinational circuits only, and that too the CMOS combinational circuits, not the other type of. Okay, so CMOS is static CMOS circuits. So you see the static CMOS circuits, as we know that the circuit works basically into two states. Whatever circuit we will take, it will work in two states. So one state is your this one static state, and the other one is your dynamic state. So static state, static characteristics is which one? Your static characteristics are the characteristics of the circuit when it is switching in the two states. Okay, in the steady state condition. So those are the static characteristics. When it is switching from one state to the other state, then you call it the dynamic characteristics, right? So the switching characteristics and the dynamic characteristics, if we talk about, so this is what happens. So we'll talk about the static CMOS circuits, in which we will assume that the circuit is like steady state in one of the this states. Okay. So static CMOS circuits are the circuits something like this, which have pull-up network and the pull-down network. So each of the network will have some inputs, and the drain combinations of these two PMOS and the NMOS networks, when you take the output from this two the drain connections of these two networks, then you get the output, and that output is dependent upon the present inputs only. So this is what your combinational circuit will look like. Okay, so the pull-up network, as we know, it is made up of PMOS MOSFETs, and this pull-down network is made up of NMOSs. The reason is that the NMOS provides you good 0, whereas PMOS provides you good 1. So that's why. Now when we have to make some combinational circuits, so what we have to do is we have to use some series and parallel combinations of NMOSs and PMOS. Okay, it's not just a single NMOS which can be used in the this pull-down network, and not only a single PMOS which we are going to use in a pull-up network. We are actually going to use a combination of the circuits, and this combination can be a series combination or a parallel combination. Okay, so if you talk about the series and the parallel combination, so suppose if we connect two NMOSs in series, then what happens? and when we connect them in parallel, then what happens, we'll try to understand them here, and then we'll do the same thing for the PMOSs as well. So you see, when we connect two NMOSs in series, then what happens, we can realize a simple AND gate, because if both the inputs are when both the inputs A and B are 1, then only this MOSFETs basically works as a switch, okay, because we are using them for digital applications, so they works as a switch. Okay, if we use them for analog applications, then they start working as an amplifier. Okay, then we have to operate in different this transistors in different range, whereas if we are using the circuit for digital applications, then we have to operate in static regions. Okay, whereas if we are using the transistor in the for the analog applications, then we have to operate in this transition region. So okay, let's see. So you see what happens, if both these switches are on, then only there will be a connection between X and Y. So if you want something at Y, something like if you want the signal at Y which is equal to the signal at X, then what we have to do is we have to make both switches on. So you have to switch both the circuits on. So when both the switches are on, then only your X gets connected to the Y, or Y will get the value of X. So that means that you have realized an AND gate with the series combination of NMOSs, right? Whereas in the parallel combination of NMOSs, what we do is, like, when either of the transistor is on, then our Y becomes equal to the X, or we get the signal at Y, whatever is available at X. So that's what the reason is. Okay. And if you talk about the pull-up network, then in the pull-up network, what happens, if we make let's say the series combination of pull-up PMOSs, then you know that our PMOS becomes on when our inputs are low. So if A is considered as high and A bar is low, so both A bar and B bar should be low. That in that situation only your X gets connected with Y, or there is a short circuit between X and Y. Okay, so you see, if you see this A bar and B bar, so you can see that it is nothing but A plus B whole bar. So by using De Morgan's, we have written this statement. Okay, and similarly, so you understand that with this thing, that if we connect two PMOSs in series, then we can realize a NOR gate. Okay, so if we connect two NMOSs in series, then we realize an AND gate, whereas if we connect two PMOSs in series, then we realize as a NOR gate, right? Whereas if we connect two NMOSs in parallel, we realize a NOR gate. Okay, if we connect two NMOSs in parallel, then we realize a OR gate. Whereas if we connect two PMOSs in parallel, then we, as per the functionality, you can see that we realize a NAND gate. Okay, so this is what happens. Now let's say this is what about the PMOS provides you the good 0, a good 1, and the NMOSs provides good 0. So this we have understood in our previous classes, so no need to go through it. But if you have any problems, you can always ask to me. Okay, so let's say from this whatever we have learned so far, now we know that suppose we want to realize a functionality with the help of CMOS circuits. So what we usually do is we realize the functionality with the help of NMOS. Okay, so the pull down network first we realize, and the pull up network will be just the dual of the pull up network. Okay, the pull down network. So the pull up network is the dual of the pull down network. So first we will realize the whatever functionality is given, if that functionality have a complete bar over it. If the function has something like y is equal to the bar of some functions written, okay, some digital expression, some boolean expression is written. So then that expression we realize it in the NMOS with the help of NMOSs for the pull down network, and then we make the dual of that. So it becomes a pull-up network. Okay, so it's not difficult, it's easy, but we'll understand it more clearly with the help of certain examples. Okay, so basically with the CMOS circuits, if you try to realize, then it is a complementary this metal oxide semiconductor this this circuits, CMOS. So you see this is basically a complementary gate. So what does it mean? That the pull-up network will be exactly the dual of that, and if if you just connect the pull-up network and the pull-down network, you'll be able to realize the function with a whole bar over it. Okay, but if you want to realize, let's say, so I mean to say that if you want to realize a NAND gate, then you can easily realize with the help of CMOS, okay, with the combination of pull-up and pull-down network. But if you want to realize, let's say, AND gate, okay, a function which is without bar, so then we have to use an inverter after an NAND gate. So then only we will be able to realize an AND gate. Similarly, if you want to realize a OR gate, then we have to first realize an OR gate, and then we have to use an inverter. Then it will become a OR gate. So it's a complementary function. So it's easy to realize the function which have the complete bar over it. So you see, let's try to understand, let's try to realize the NAND gate. So let's say with the help of CMOS. Okay, so CMOS, this MOSFETs. So if you want to realize any gate or any function, so first of all we have to draw its truth table. So if we write the truth table of this function, this NAND gate, then we can see that the truth table will look something like this, isn't it? When both the inputs are 0, then the output is 1, and when either of the input is 1, okay, when either of the input is 0, then the output is high, and when both of the inputs are high, then at that time the output is low. Okay, so let's say this is a 2-input NAND gate. So we have written the functionality like this, but if it is a more than 2 input, then also the same logic applies. So whenever all the inputs are high, then only the output will be low, else when either of the input is low, then the output will be high. So this is what your NAND function is. So if we realize it, then we can see that if we try to understand it from the truth table itself, then we can see that our this circuit should be, this pull down network should be, because why I am talking about the pull down network, because we want 0 at the output. So the 0 at the output will be realized when the output gets connected with the ground. So to connect the output with the ground, what we have to do is we have to use two NMOSes in series, because we want both of them to be on simultaneously, as it is a 2-input NAND gate. So we have used two NMOSes. If it would have been a 3-input NAND gate, then we will use 3 AND gate, 3 this NMOSes. Okay, if it is n inputs, then we will use n NMOSes in the this pull down network. Okay, and in the pull up network, if I talk about, so pull up network is exactly the dual of that. So when I say dual, a dual of that, so what does it mean? The dual is, if the NMOSes are connected in series, then the PMOSes will get connected into the parallel. Okay, if whichever in the pull down network, whichever MOSFETs are connected in series, if you apply some inputs, let's say A and B to the NMOSes. So if this MOSFETs, these NMOSes which are getting the inputs A and B, those MOSFETs should come in parallel in the pull-up network. So that's what the logic is. So when you do this, then you call it a dual network. Okay, so if we do this, then we will realize a NAND gate, and you can verify this the circuit with the help of truth table as well. So you can see that when both the inputs are 1 1, at that time what happens? If both the inputs are 1, at that time this your NMOSes, both the NMOSes will be on, and your output gets connected to the ground. So there will be a direct connection between output and the ground. Okay, so output will get discharged through this, right? Whereas if you apply, let's say if one of the input becomes 0, then what will happen? If let's say this one of the input becomes okay, I'll erase it first. Let's say one of the input becomes 0. So then what will happen? If let's say this input is 1 and this input is 0. So if this input is 0, if whichever input is 0, then the this two series NMOSes there'll be no direct path, okay, no short circuit between output to the ground. So in such situation, one of the NMOS it will be off, and if it is off, then there will be no direct path, and the circuit, the NMOS network will not work. Okay, so it will off. It will remain off. So the output cannot be 0. Okay, that is for sure. But when you now I will analyze the pull-up network. So when you connect the pull-up network 1 to the pull-up, when you have made the inputs 1, so at that time what happened? At that time your both the inputs are 1, then what happens? Your both the PMOSs are not working, so they are in cutoff. They works in the cutoff region. So if both of them are cut off, so obviously ground the output is connected to the ground. But if one of them is 0, okay, if one of them is 0, then what happens? If let's say this is 0 and this is 1, then what will happen? This particular whichever input is 0, that transistor will be on, whereas the other transistor will be off. But if both the inputs are 0, then no problem, both the transistor will be on. Okay, although there will be a little difference in the resistance, because in the worst case scenario, one of the transistor will work, whereas in the best case, both the transistor will be on. So amount of current which will flow through the path will be different, but if you try to understand the logic, then we know that if any of the transistor gets the input 0, if any of the transistor, whichever transistor gets input 0, that transistor will be on, and there will be a direct path from VDD to output. So the output will get charged to 1. So easily you can realize that your circuit is now properly working as a NAND gate. Okay, so you see, this is how you can analyze the circuits. Now let's move on to the other circuit, and let's say you want to realize a NOR gate. So 2 input NOR gate. So whatever we have understood in the above slide, so same things apply here as well. So what we have to do is, let's say first we make the truth table. So whichever gate you want to realize, first make its truth table, and then just see that whichever combination you can apply. So you see, in this case, if both the inputs become 0, then your output should be 1. Okay, so output should be high when both the inputs are 0. So when this condition arises, so it means the output should be connected to the VDD. If your output is becoming 1, then it means that the output should be connected to the VDD. Okay, so when the output will be connected to the VDD, only in situation when both the PMOSs are on. Okay, and when both the PMOSs will be on, when you give the 0 input to the 0 as the input to both the PMOSs, then only your both PMOSs will get on. So you see what will happen, you have to connect the 2 PMOSs in series. Okay, so PMOSs gets connected in series. Similarly, if you analyze the other half, so this functionality, if you try to, the pull down network will be the dual of the pull up network. So whichever you realize, then the other one will be the dual of that. So I tried to explain this in one way, but the other way, if you want to understand, then the functionality of a NOR gate looks like A plus B whole bar. So if it looks like A plus B whole bar, then that particular function should come in the pull down network. So A and B will be in parallel in the pull down network. Okay, and in the pull up network it will be the dual. So you will connect them, the PMOSs, in the series. If NMOSs gets connected in parallel, so then the PMOSs will get connected into the series. Okay, so this is what you do, and then the same way which we have used, you can realize, you can understand this particular thing as well, that how it is working. Okay, now the important thing is the calculations related to the threshold voltage and the other calculations, like this threshold voltage is your VTH, whereas you can calculate the other parameters like VIL, VOL, okay, VIH, VOH. But the thing is, it will be difficult for us to calculate VIH and this VIH and these other parameters, VIL and VIH. Why it is difficult? Because the transistor operates in different regions. So for this particular course, we will not consider those VIL and VIH calculations. VOL and VOH we easily know that because it is a full voltage swing. This CMOS circuits provides you full voltage swing. So whatever supply you will apply, so that will be your VOH and VOL. But to determine VIL and VIH, we have to analyze the circuit in various regions. So we won't do that here because this is an introductory course of this your VLSI. So we won't do those things here. But if you try to realize if you want to find the threshold voltage of this any gate, okay. So let's say if you want to determine the threshold voltage of this NAND gate, so how we can do it? So to understand this, what we have to do is threshold voltage. Okay. So whenever we talk about the threshold voltage, it is the voltage. If you just recall your the CMOS inverter VTC, then you can you know that it looks like something like this. So how your VTC looks like? So it looks like something like this, isn't it? So you see where your threshold voltage falls. So it falls somewhere near here. Oh, sorry. So your VTC looks something like what? So it looks something like this, right? And your VTC falls somewhere in between. So you see, this is our output terminal we have plotted here on the y-axis, whereas this is our input. Okay, so this is input and this is our output. So this is our VTH. So we know that for an ideal the CMOS inverter, our VTH should be somewhere between VDD by 2. So if this is our VDD, if this is my VDD, then this should be VDD by 2. Okay, so you see VDD by 2, and at this point your input is equal to output as well. So V in is equal to V out. Okay, so you see if we keep this into mind and we analyze the circuit, then we understand that at threshold voltage what happens is our inputs A and B both are at VDD by 2. Simultaneously the output F is also at VDD by 2. Okay, now what we further assume is that our devices are of equal dimensions. Both the NMOSs are of equal size, W by L, okay, and the PMOSs are also of the equal dimensions. Okay, so W by L of this A PMOS is equal to the W by L of this B PMOS. Okay, and similarly of the NMOSs as well. So we assume this, and we assume that the inputs are also equal, V and VB. So at threshold voltage, VA will be equal to VB, and that will be equal to your V out, because VA and VB is equal to V in. So V in is equal to V out. Okay, so VA is equal to VB is equal to V out, and both of these are equal to what? VDD by 2 or VTH. Okay, so VDD by 2 I have told you ideally for in case of inverter. For a CMOS inverter, if we just want to find this the threshold voltage, at which voltage it will get it will switch, okay, from on to off. So that's what we have to find. So we have to find the formula for that, okay, VTH formula. So what happens at this VTH? So if we try to find that in which region particular our transistor operates, so we have to find for every transistor we have to find the region in which region that transistor is working. So let's start with NMOS first. So you see your NMOS source is connected to, if I talk about the NMOS, so then your NMOS source is connected to ground, right? So NMOS source is connected to ground, whereas the drain of the NMOS is connected to, let's say, some voltage which is equal to VTH. Okay, so VTH, because now as the device is threshold, this is at threshold, is just working at that VTH, so then your output will be equal to VTH and inputs will also be equal to VTH. So if input is also equal to VTH and output is also equal to VTH, so then you see what happens, your VGS, gate to source, so VA and VB both are equal, and let's say both of them are equal to VTH. Okay, so VTH and output is also at VTH. So my point is your VGS will be equal to VTH, that is gate to source voltage, because source is ground and A is connected to VTH. Okay, the input is becoming VTH at that instant. So VGS is equal to VTH. And output, which is drain to source. So output is also at VTH. Okay, we want to find this VTH voltage. So at this point, your input and output both are equal. So Vout is also at VTH. So VDS will be also equal to VTH. So you see, your VGS is equal to VDS. Now whenever this situation arises, then we know that our transistor operates in saturation region, right? Not in the linear region. So both the transistor, both the NMOSs, because you see they are connected in parallel. So each of the transistor, each of the NMOS will work in the saturation region. So that's what the reason is. Okay. So both of the transistors, both of the NMOS will work in the saturation region. Whereas if we talk about the pull-up network, so then how we can find it, that in which region they are operating? To find that particularly, that in which region this transistor PMOS to which A input is connected and the other PMOS to which the B input is connected, in which region they are operating. So how to find it? So let's try it. Okay, let's try to understand that. And that is like little tricky, okay, to understand. So be attentive here. So you see, what we have to do is, you see, if to understand it, let's assume that the resistance offered by the two devices, two PMOS, is equal. So if the resistance offered by the two devices, two PMOSs, is equal, then the voltage drop across the two devices will be equal, right? So if your the source of the B PMOS is connected to VDD and the drain of the A PMOS is connected to output, then what we have to do is, you see, if this is connected to VDD and the other one is connected to VDD by 2. So this first one is connected to VDD, BMOS, this B PMOS is connected to this source of PMOS, or the upper transistor, source of the PMOS of the upper transistor is connected to VDD, whereas the drain of the lower PMOS is connected to the VDD by 2. And if these resistances are equal, then the voltage drop across each of them is equal. So if this is VDD, this point is VDD, okay, the upper point is VDD and the lower point is VDD by 2, and the drop is equal. So what will be the voltage at this point? Okay, so you see, this point will be, if this point is VDD, this point is VDD by 2, so this will be what? In between them. So in between them is 3/4 of your VDD, right? So let's assume this. So this is the 3/4 of VDD, okay, in between them. So you see, in between them, if it is 3/4 of VDD, so now you try to understand. So you see, the voltage drop across each of them is 1/4 of the VDD. So the total voltage drop is VDD by 2. So the voltage drop across each of them is VDD by 2. So I have assumed as that half is dropping across this and the half of the voltage gets dropped across the lower one. So now you see, if again we will use the same logic. So this particular point, this middle point is at 3/4 of VDD. So if this is at 3/4 of VDD and your A is at VDD by 2, okay, so this is your gate and your drain. So gate to drain, okay, gate to drain we don't consider, we consider gate to source and gate to drain. So gate to source, gate is connected to VDD and the source of this lower transistor is connected to 3/4 of VDD, okay. Whereas if you consider the drain to source, then drain is again the output of the lower transistor, so that is also connected to VDD by 2, because we want to analyze this transistor is operating at the threshold voltage, the circuit is operating at the threshold voltage. So the input and output are equal. So this F is also equal to VDD, this VTH by 2. Oh, sorry, VTH. So this is also equal to the same voltage. So this is VTH and that is also VTH. So both the inputs, see, drain to source, drain is at VTH, gate is also at VTH, source is at 3/4 of VDD. So you see, both VGS is equal to VTH. So this transistor The lower transistor, lower PMOS, will work in the saturation region. Okay, whereas if you want to analyze the upper transistor, so let's try to understand that as well. So what will happen in this case? Your B is at VTH. Okay, whereas this gate to source, if you talk, so gate to source, so source is at VDD, whereas this is at gate is at VTH. So what is your gate to source voltage? So it is minus VTH. Okay, because okay, VDD minus VTH, you can say gate to source, so VTH minus VDD. Okay, whereas if you talk about source to drain, okay, because you have to see this as well, so gate to source and this the other one, source to drain. So you see this one, so in this case gate to source and your this other transistor. So for this case you will see that this particular is not satisfying this saturation condition, and your this difference gate to source is not equal to your gate to drain to source. Okay, so you see they are not equal, and as you can see that your PMOS operates in your linear region. Okay, so as your PMOS operates in your linear region, so you see this one, so your PMOS transistor, as we have discussed, the upper PMOS transistor operates in the linear region. Okay, the BMOS, this BPMOS. Why? Because the difference between the gate and source is less than that of the drain to source. Okay, so if this is the situation, if VDS is less than VGS minus VT, then obviously your transistor operates in the linear region. So in this case you will see that your VDS, drain to source is 1/4 of your VDD. Okay, 1/4 of VDD, so that voltage drop is 1/4 of VDD, whereas this is VGS VDD minus VGS. Okay, so VDD minus VDH, so that will be obviously this one is greater than, so gate to source is greater than your drain to source. So if gate to source is greater than drain to source, then obviously your transistor operates in the linear region. So because to satisfy to operate in the saturation region, your drain to source voltage should be greater than VGS minus VTH. So this is not satisfying that condition, so that is why your PMOS operates in the linear region, right? So BPMOS operates in the linear region, whereas APMOS operates in the saturation region. So now once you understand that clearly, then there is nothing new. The same thing which we have done earlier, we have to do again here. Whatever we have done for the CMOS inverter, the same thing we have to do here as well. So you see, we will write the drain current equation for both our PMOSs, NMOS, PMOSs, APMOS and BPMOS, and the saturation current equation for your NMOS. So as our BPMOS is operating in the linear region, so we have written the linear region equation for that. Okay, whereas the APMOS is operating in the saturation region. Okay, so we have written the saturation region equation for that transistor. Now as you know that our transistors, both the transistors, they are in series, so whatever current is going to flow from the B transistor, the same current is going to flow from the A transistor as well. So if we equate both the current and we solve it, then we find that our VDD is equal to this in terms of this. And similarly, if we find that our whatever current is coming in this node is getting divided into this IDB and IDN, and if you write this equation of these two transistors as well and substitute the values from the other equation of VDD and this VTH, then we find that our this particular thing, this VTH of NOR gate, comes something like this. Okay, so you see this equation is similar to the threshold voltage equation of your inverter. The only difference is that in that equation there was no 1/2, but whereas in this equation there is 1/2. Okay, and this 1 by 2 is because of this 2 input gate. If you would have used n input gate, then this would become 1 upon n. So that you should keep into mind. So that 2 comes from the number of transistors. So if suppose you want to find the threshold voltage for 3 input this NOR gate, so then the 3 input NOR gate VTH will have same expression but with 1 by 3. Okay, so you can try it out. Okay, so this was the thing for this thing, and it is compared with your VTH of inverter. So you can see that the expression looks more or less same as that of the inverter, but there is a little difference. Okay, now for the case of when your Kn is equal to Kp, that is your this particular case when Vtn is equal to Vtp, at that time if you find this VTH of NOR gate, in such a case your VDD, this VTH of NOR gate will be VDD plus VTN by 3. Okay, and we have assumed that our VTN is equal to VTP. Okay, this is the case of your symmetrical inverters, right? Now there is other approach as well, but to understand that approach we have to first understand that what happens when you can determine whatever we have determined by finding the various regions in which our transistor operates. You can find the threshold voltage by, if you know the formula for your threshold voltage of the inverter. Okay, and if you just convert the circuit in the form of an inverter, whatever circuit you have, because this whatever circuit, let's say this is an OR gate, so whichever gate you have, so that circuit will always have some pull-up network and some pull-down network. So if you replace the pull-up network with a PMOS, let's say, you consider that it is a single PMOS, and a pull-down network consists of a single NMOS. So if you assume this, then what you have to do is you have to write the equivalent W by K of this transistor, which you are assuming that this is a single transistor. So there are multiple transistors. So you are assuming that this multiple combination is replaced with an equivalent single transistor. Okay, single PMOS or a single NMOS. So but then in that case, if you assume that it is replaced by a single transistor, then you have to find the equivalent this K ratio. Okay, Kn or Kp ratio for that transistor. So how you can find that equivalent ratio? So you see, I'll try to explain that in short. But you see, if you, that you can understand very easily with the help of resistance diagram. So if I assume that as you know that in case of your NOR gate, your NMOSes comes in parallel. So if I draw two resistances in parallel, then you see what happened. And if I assume that the resistance of this device depends upon W by L. Okay, so you see, length remains same, whereas the width is becoming double. So if I write Kn is like function of, because the other things are like constant, mu and Cox. So if I assume that it is proportional to W by L. So if L remains the same, and in usually any design we keep L minimum. Okay, so L we always keep minimum. Now we have only think W. Okay, we only have W to change. So we can change W. So you see, if our L remains the same, then what will happen? Our W is becoming twice. So actually our Kn is becoming twice. So the equivalent Kn of this combination will be actually 2Kn. Okay, so that is what we have seen. So you see, that's why we have written twice of Kn. So if you want to replace the whole pull down network with a single transistor, so then the width, the WL ratio of that transistor should be the twice of the WL ratio of a single transistor. So single transistor WL, transistor WL ratio I have expressed, let's say, by Kn. So the Kn of the equivalent transistor will become 2Kn. Alright. Similarly, if we try to find the equivalent Kp of our PMOS combination, so then you see, for a NOR gate, the PMOS will come in series. So if I replace each PMOS, they are switched. So if I replace them with a resistance switch, let's say assume that it offers some resistance, each of the switch offers some resistance. So in this case, when the two PMOSes are connected in series, then in this case, if you find the equivalent K, Okay, equivalent this Kp for this. So let me erase this and do this again. So what we do is we find the equivalent Kp for this combination. So what will happen? Let's say the Kp of each of them is each of the transistor is Kp. So what will be the equivalent Kp of this two? So you see, if we connect the two transistor in series, then width, let's say width doesn't change, width remains same. Okay, because the current will have same will get same thickness to flow. Okay, so that is why I am saying that the width remains unchanged, but it has to travel longer path. So then I will say that the length gets double. Whereas in the previous case, when we have considered the NMOSs, then we get two parallel paths. So actually the width is increasing. So width is becoming double, whereas it has to travel the same length. So that's what I have considered. So let's say again, if I write this K is proportional to W by L, and as I am saying that width remains unchanged, but your L becomes double. Okay, so L will be double for equivalent. So what will happen in case of equivalent? If I assume the W by L of single PMOS is equal to, let's say, Kp, so then the equivalent Kp will be equal to how much? Kp by 2, right? So it will become Kp by 2. This is how you can write. So this is what is written. So if you write this thing, then your transistors will be these equivalent transistors will be of such a ratio. Then there is nothing. Now if you remember the equation of your threshold voltage of your CMOS inverter, then you can substitute the Kn and Kp values of this particular transistor, this equivalent transistor, in that formula, and you can easily get the this function of VTH. Okay, so it is the other way to find this. So whichever way you want, you can do it, understand it, but depending upon in the exam, if it comes, so you have to see the marks distribution, and accordingly you have to see the formula, which method you should use. Or otherwise, if it is specifically asked that you have to derive the formula with this particular method, then you have to use that method. Okay, so it depends upon that. Okay, so let's see the threshold voltage of the, we have seen the threshold voltage of our NOR gate. Now let's try to see the threshold voltage of our NAND gate. So first of all, we have seen that how our NAND gate is realized. So this is the same slide which we have seen earlier. Now if you want to find the threshold voltage of the NAND gate, then again the logic is same. In the first case, what will happen? If you consider the VTH, then your both the upper transistors, both the PMOSs will work in saturation region. Whereas here in this case, your this NMOS will work in linear region, whereas your A NMOS will work in the saturation region. Okay, so the same understanding which we, the same logic which we used there in the PMOS, same logic if you use here, you will find that the threshold voltage of your NMOS comes something like this. Again, here difference is, there it was 1 by 2, now it becomes twice. Okay, so you see that 2. Okay, again this 2 comes from the number of transistors you use. If you use 4 input NAND gate, then it will be that number will be 4 here. Okay, so you can find it, right? And similarly you can find it by the equivalent method as well. Okay, so here I stop over today's lecture. So with this we'll stop over today's class. In the next class we'll do the other half of this. So the other half is not that much mathematical, but it is interesting as well. So we'll see that other half in the next class. So I stop this today's class here itself. So thank you to all for listening. Thank you very much.